Hello, guys. I'm Tomek, and I'll be speaking in English because that's the language I've prepared my presentation in. If you have any qualms with that, I'm sorry, but this is how I do it. I'm from Kraków, as Przemek said. I came here specially for you. And this presentation has never, ever been done anywhere else, apart from PyConic in Kraków. So if you have seen it, then you have 25 minutes of free time. OK, few words about this presentation. This is disclaimer. Every code here that was executed and its output presented was run on Ubuntu 12.04, 64 bits, and with cPython 2.7.3. It's a quite important information because it doesn't apply to other Python implementations like PyPy and Jython. I'm not an expert in cPython, especially cPython internals. I don't really know how it works. I use Python and I'm proficient with Python. I never have written any C line that works together with Python. Whatever I talk here about, it is much more complicated than I present it. So, take it with a grain of salt. And on some level, this presentation should be called I don't even know what I'm talking about. OK, so this talk is a case study. I work with Python. I'm a web developer. We have long-running processes in our company. And at some point, I thought that my processes are taking too much of the precious memory we give them. It took me a long, long time to decide that I really want to go and investigate why the memory usage is sometimes so big, instead of just randomly killing the processes, because that's faster. But at some point, my boss said, well, we need to cut costs of our servers, so let's do this. So as I said, the case study is like follows. We have long-running processes. They take memory at some point, and then they never release it. You can actually argue now, well, why do you take so much memory in your web processes? So you should probably do this work in a background thread or something. Well, yes, but the application I'm working with has some history, and it's not easy to change the history. I'm working on it, but it's a process. I've worked long hours. I think it took me 3 days to get to the bottom of this problem. And I've tried many tools, too many of them. It's just amazing how many there are, and it's equally amazing how many crappy there are. But as you will see later, I only found one tool that's helpful. After 3 days of swearing and being closely crazy, very close to going crazy, I've boiled down the code to something like this. The process allocates a boatload of memory. The alloc function here is a sample function that allocates 100,000 strings, each of 5 kilobytes. So that's roughly half a gigabyte of memory, which represents what the application was doing. It was very stupid. But report function will just report the memory usage on the output. Then the third line allocates a little bit of memory more, just one string. That's it, nothing more. After that, I no longer have use for the big list of strings, so I dereference it. This here it's just del keyword, so very simple. You could do it if you did the calculations in a separate function, then you could just let big slide out of the scope, and that would serve the same purpose. And after that, I report what the memory usage is. So after boiling code down to this and then seeing this output, I was quite annoyed because I didn't really know what's happening. As you can see here, after allocation of big chunk of memory, we have half a gigabyte of memory used. And this here is a memory used as reported by the system. So the method used here is just looking at the /prots/self/status, which has all the nifty-gritty details of how kernel sees your process from outside, so to say. So the first line is as we expected, or as I expected, which was fine. But the second one was not. At this point, I've started thinking of committing suicide, but then I've remembered that, Python is a dynamic language. I use it because I don't like to fiddle with memory and with pointers and stuff like that. So it has to do something about memory. The normal way to go about this is to use reference counting. So every variable that you have, or every object that you have in Python has a reference count that roughly is equal to number of ways you can access this object from your code. Of course, this is simplification because if the reference count goes to 0, then Python knows this variable is no longer used, and it can release the memory. Good. Some data structures are self-referential or can create cycles, and if you have A pointing to B, B pointing to A, and then you forget this cycle, the reference count on these objects will never go down to 0. So Python also has a garbage collector. That's quite simplistic, but works well. So at this point, I was thinking, well, maybe my list is somehow magically creating reference cycles. So I decided to knock the problem on its head with a hammer. So I've imported GC called GC collect. Number 2 here is the last number I've tried. The number here determines which generation you want to collect. I've tried all three generations, so 0, 1, and 2. But frankly, I got this. I mean, after running garbage collection, the program was using more memory. Slightly more, but still more. So at this point, I've actually started getting interested in this problem because, madness being really nice and cozy place, I've started thinking, well, maybe there's something much deeper here. But I was not willing to go there alone. So I've started looking for friends, and by friends I mean tools. As I've said at the beginning, I've tried roughly 10 different tools, and none of them helped me a bit. After that, and some drinking and some crying, and one more day spent on looking at this code, I've decided that I've interpreted some of the tools badly, and I've looked at them once again and discovered that one of the tools is actually genuinely helpful. I was just stupid not to believe it. So enter Guppy. It's a small library. You can download it from PyPI. Just pip install Guppy. That's it. This is the only tool that gave me some help. Probably because I was stupid, but also because most of those tools have absolutely no documentation at all. And the only thing the only way you can know what you're doing is just look at the code or look at the output of what it's telling you. But sometimes those are just very shortcuts of three letters, and you have no idea what it is, or at least I didn't have. It's available on SourceForge. It's open source. As I said, documentation, it's not the greatest point of this library. But after some staring it down, you can work with it. So how do you use Guppy? You import hippie. That's what the documentation say to pronounce it. So you import hippie, and then then you ask hippie to create a snapshot of your heap, and then you take the topmost objects. The heap is by default sorted by memory usage, so you will have some happy output in there. This is how the output looks like. I've edited it somewhat because it's dense here, but yeah, this is how it looks like. It gives you rough overview of what your Python is doing with objects you've created, or Python itself has created to manage itself. As before, there are two sections here. First one is just after allocating the big chunk of memory, and the other one is just after using the del keyword. So we see here that after allocating, we have 500 kilobytes used. Again, this is the what the system reports the program is using. Then we have total number of objects being tracked by Python, and that's 1100,000 objects. And the total size is what Python knows about those objects. So this is what Python reports that it has, and it's roughly half a gigabyte. So more or less what we expect. And the table below describes what we expect here, right? We have 11,000 strings. Although we only allocated 100,000, we have 110,000 of those strings, and the cumulative size of those strings is roughly 100% of the program. The interesting bit is the second invocation of this. After using del keyword, the program, as reported by system, is still using half a gigabyte of RAM, but uses only 15 megabytes of memory that's available to Python, or that Python knows of, that Python tracks. And we have only 10,000 strings, which is correspondent to the amount of strings we released, right? We had 110,000 strings before. Now we have 10,000, so we released 100,000 strings, which is good. So now, why does system tell me I've kept 500,000, half a gig of RAM? Because obviously I did not. At this point, I've started looking, searching back my memory, and I've remembered something I've learned years ago during the university time, and it's called memory fragmentation. So before I talk about what memory fragmentation is, let me just remind you how the kernel, the Linux kernel, treats your program. There are a couple different kinds of memory you can request from the kernel. But the most important one, the one that you use mostly working with in Python, is the heap. And you can imagine that heap is a continuous memory space, memory that's allocated only from one side. Let's say right side. So you allocate a big chunk of memory there, and then you allocate some small, but it can grow only from one side, and it can only shrink only on that side. So if you deallocate the big chunk of memory, this memory is free, but as you can only shrink the memory from the right side, the kernel cannot take it back, because that would require the kernel to say that the address space of your process has to change, which is not really easy. So I thought, yeah, this is why I have this problem. This is why the process is leaking memory and never releases it back. But it turned out it's not really, because I've tried to remove the small allocations I did after big allocations, and it never happened. The memory was never released, which at this point I thought, well, I'll be drinking more whiskey tonight. After drinking some more alcohol and sobering up, I've started Googling, asking questions, trying to find some traces of what the hell can be happening to my program and how can I stop the pain. And I've learned that Python does not use the memory allocation system call directly. So if you allocate new objects, the Python doesn't go, malloc and then here's space for your program. No, because Python objects are way more complicated and not simple C structures with some type attached to it. No, Python has somewhat complicated memory allocator, at least in 2.7. In Python 3, it changes a little bit, but I don't want to go into that right now. So Python uses something called arenas, which store pre-allocated memory. So if you want to have a list, Python's first searches in arenas that it has previously allocated. If there is some unused memory, like just the memory we have seen, the one that you've deallocated and was never released to the system. And if it finds it there, it gives it to you. If not, then it allocates new arena, and then gives you the memory from there. Sometimes it's called also free lists. I didn't find any particularly good source for reference here, and the more I looked, the more people told me, go and look at the source code. This mechanism is most important for lists and dictionaries and frames, which are what the function call is actually recorded by the interpreter. So, and as written here, it speeds up the code execution immensely. I've read somewhere that the speed boost after implementing this was somewhere around 3 times, but I cannot point you to the link because I was probably too drunk to remember it. So the free lists that Python keeps together contain objects of similar size. So to test this problem, I've created a free list torture. So this program allocates 500 lists, and each list is bigger than previous one by 1. So almost every time that Python tries to find the list in the free list arena, it's not there because the previous lists were smaller, so it has to search further and allocate more memory. And if you look at this program, it's roughly correspond to the first one. First, I allocate some big amount of some big chunk of memory, and then I delete it and report the usage. But there's no small allocations between them. So the allocation, deallocation, that's it. There's no tricky part in there. And after running it through Python, it looks like that. This never happens. The memory is never leased. And here I knew that this probably is my problem, and I'm not going to be able to fix it using stock Python methods, and I will have to deal with something else. And my boss told me, yes, that's true. So go and find some solution, because we cannot have this happening in the production anymore. Okay, well, I've made a list of recommendations. First one, we write this whole stuff, and we'll be happy with this ever again. And my initial estimate of work required was so high that my boss told me a stiff no. Then I tried to fiddle with sub-processes and actually offloading this memory intensive work to some process that can, some other process, so we can reap this process and never have to deal with cleaning up. The system will clean up the mess and we'll be happy. This was actually the solution we used and we were happy about because it was understandable. But I found the even more interesting option here, and it's called, I don't even know how to pronounce it. I will pronounce it gmalloc. Gmalloc is alternative implementation of malloc system call, or it's not even system call. It's a standard C library call. It implements the same interface and is actually a drop-in replacement. Considering how the shared library mechanism in Linux works, there is a method to force Linux to preload a library before running your program so that some symbols are available. And then when your program looks for some other symbols, they are there, so it doesn't load anything else. So if you preload gmalloc before your Python, it will not use system malloc, and you will be happy because this implementation is much more sophisticated than Ubuntu stock glibc malloc. It uses many heuristics to keep your objects in good shape and your memory not fragmented, and so on and so on. This is way more advanced than I wanted to know, but still I will present you the solution how to make your program behave better, somewhat. At the top we have the same output that we had before for the first version of the program. As we can see, half a gig, nothing is released. After preloading this malloc library, we see different things. First of all, the top memory use is way higher. That's 60% more memory. So if you use this, you have to be prepared to have, at peak times, have more memory. If you're as stupid as me to have half a gigabyte memory in your web application process. But after deleting and releasing the strings, the boatload of strings we had there, it actually cleans up pretty well. We only have 11 megabytes of memory left, so that's almost nothing. And after running GC, that's a couple of more megabytes less. As far as I know, I think Facebook is using gmalloc for pretty much everything, but that's not official information I got from any Facebook employee. But they have a pretty good coverage of changes they made to this library, so it's probably true. I've seen also many people recommending this with MySQL because it's not a really good program and doesn't have good memory management. So this might help you. Okay, time for some conclusions. Sometimes memory leak is not what it seems. Sometimes you have to dig deeper and maybe not blame stupid programmers. Maybe you should blame yourself and your code, or not. Or maybe it's your interpreter going into your way. As I said, I'm using Python because I don't like dealing with memory cleanup and initialization and stuff like that. It bores me. Malloc is not the best of breed. So glibc is not the best of breed. I've read some stories about bad maintainers there. Well, it happens. The curious thing is that when I wanted to show this to my girlfriend, I brought this code with me to home, and I happily ran it on my Mac, and nothing happened. I mean, the code did what I expected it to do, so release the memory instead of keeping it as they did at work. And it turns out Mac has different malloc implementation, which is roughly based on gmalloc, and works better. Dealing with memory-intensive stuff in sub-processes has many advantages. Not only it frees your processes to serve web requests, but also you don't have to deal with this shit. One other thing I've noticed debugging this is I had way more erratic output from my debugging statements when I was still running the code through Apache and ModWhiskey. ModWhiskey is C extension, and it's written probably well, but at some point they're bound to have some memory leaks, or maybe not memory leaks, but they're not using memory in a way I would like. So I've stopped using that, and it also helped. Okay, that's it. Thank you for listening to this rambling. Any questions?
What was the time difference between executing malloc version and
I didn't measure that. I don't know.
Was it significant or not?
I don't know. It was roughly 1 second for both, but don't take me on it. I didn't measure it.
Jesteśmy w Polsce, to pozwól, po polsku.
Śmiało.
Krótko. Głównym wyznacznikiem, który tutaj przyjąłeś, było zwracanie pamięci do systemu.
Tak jest, tak.
Dlaczego?
Ponieważ...
Ale wiesz, że to jest kosztowne, zarówno zwrócenie jej, jak i później zaalokowanie.
Tak, zgadza się.
Który jest cachowany w pewnym sensie przez malloca, ewentualnie przez Pythona. Python po to ma właśnie pulę pamięci, żeby za często się nie odwoływać do systemu.
Zgadzam się, tak. To było związane z tym, że te pół gigabajta, które program zjadał, było nieadekwatne do tego, co normalne działanie tej aplikacji wymagało, a wymagało 70 megabajtów. Więc żeby to się mieściło w naszym capacity plan, chcieliśmy zrobić, że owszem, proces ma możliwość zaalokowania sobie pół gigabajta pamięci, ale niech ją odda po zrobieniu całej tej operacji, tak żeby inne procesy mogły to zrobić. Ta operacja była rzadka, powiedzmy raz dziennie ktoś wykonywał ten request, który powodował i byliśmy w stanie zapewnić te pół gigabajta, ale tylko jeśli te pół gigabajta ten proces odda później, bo powiedzmy mieliśmy tych procesów 10, jeśli każdy zajmie pół gigabajta, to mamy 5 gigabajtów. Tego nie chcieliśmy im dać. Znaczy tyle pamięci nie chcieliśmy dać, więc chcieliśmy, żeby ta pamięć była odzyskiwana. Bo większość tych requestów nie potrzebuje pół gigabajta, potrzebuje 70 megabajtów, może 100, a nie więcej. Tam z tyłu? Testowałem to na innych wersjach kernela, ale nie dużo innych. Testowałem to na Debianach, no i tak jak mówię na Macu wszystko było pięknie, na Debianie wszystko było identycznie. Testowałem to też na wersjach innych Pythona. Z ciekawości odpaliłem to na PyPyu, żadne tego typu problemy nie miały tam miejsca. Odpaliłem to na Pythonie 3. Efekt był lepszy niż odpalenie na Pythonie 2.7, ale dalej jednak niesatysfakcjonujący. Nie odpalałem tego na żadnych Fedorach ani niczym takim. Na Windowsie też nie próbowałem. Nie mam nawet. Jeszcze tutaj.
Czy ta implementacja oparta na RN-ach, tak, do oszczędzania pamięci, do oszczędzania mechanizmu alokacji i dealokacji, to jest coś związane z cPythonem? To jest tak, że cPython tak zbudował całą abstrakcję na dealokacji pamięci, czy no bo pokazałeś patch, który robi to na mallocu, tak jak to miał mechanizmy systemowe, tak? A abstrakcja jest w Pythonie, tak?
Okej, to żeby szybko odpowiedzieć. Tam jest kilka warstw. Pierwsza warstwa jest taka, że kernel ma jakiś tam wskaźnik, gdzie się twój program zaczyna, gdzie się zaczyna sterta, heap i jak dużo tej sterty masz. Na tym się rola kernela kończy. Dalej malloc ma jakąś tam implementację tego, w jaki sposób, jak chcesz pobrać 5 bajtów tej pamięci, to co zrobić, żeby nie walić ciągle syscalli do kernela. Więc on tam sobie jakieś rzeczy robi. Malloc, ten tutaj, który prezentowałem, robi sztuczki podobne jak Python, to znaczy właśnie alokuje sobie jakieś pule, używa tam tego mappa i innych rzeczy i dopiero przekazuje to do twojego programu. Jeszcze nad tym poziomem jest poziom Pythona, który implementuje właśnie znowu pule, areny i coś podobnego. Jeszcze kilka innych sprytnych rzeczy. Choć nie nazwałbym tego jakoś super skomplikowanym, bo jak patrzyłem na tą implementację w kodzie, to jest funkcja, która ma tam chyba 300 linii kodu i tyle. I to jest cała implementacja pamięci w Python. Nie wiem, nie mam pojęcia. No, tak jak mówię, PyPy nie miał tego typu problemu w ogóle.
No ja rozumiem, że to był problem w lipcu, prawda? Implementacji. Co?
To problem był tak naprawdę na dwóch poziomach. Tutaj w prezentacji tego nie widać. Tak, dokładnie. No jakby nieszczęśliwe złożenie różnego typu niekompetencji, począwszy od glipca, interpretera Pythona, aż po niekompetencje programistów programu, który zaprezentowałem, czyli mnie.
Myślałeś o tym, żeby zabić proces, jak ten request przyjdzie, jak on przychodził raz dziennie, to mógłbyś go po prostu zabić.
Tak, takie było nasze początkowe rozwiązanie, ale ono nie działało dobrze. Bo ponieważ używaliśmy mod WYSIWYG i z jakiegoś powodu takie randomowe zabijanie tych procesów przez zewnętrzny proces nie działało dobrze. Z wewnątrz też...
Wiesz, który request powodował, mógłbyś sam się zabić.
To też nie działało to dobrze. Bardzo konfundowało to mod WYSIWYG. Teraz przeszliśmy na G-Unicorna i wszystko jest złoto, więc... Dobra, tak.
Dobra, chciałem cię zapytać, pokazałeś, jak iterowałeś, czy tam czyściłeś jedną generację pamięci. Ile ich jest? Jak one są?
W Pythonie są 3 generacje, 0, 1, 2. 0 to są obiekty, które dopiero zostały zaalokowane. Generacja pierwsza to są te obiekty, które przeszły test 0.
Jeden cykl, tak? Jak przeszedł.
Jeden cykl, a 2 to te, które żyją już dosyć długo i nic ich nie zabiło do tej pory. Z ciekawostek, no w Javie alokator pamięci jest na tyle sprytny, że potrafi sobie obiekty w pamięci poprzesuwać i tam ten problem w ogóle nie występuje już na poziomie alokatora pamięci. Występuje, tak?
Troszeczkę w innej formie, ale faktycznie to też...
Masz tam 7 generacji różnych,
Dokładnie
one
o to
jak
chodzi.
dotrą
Masz
po prostu
przesuwanie.
kilka cykli.
No właśnie.
Z starszej generacji jest przesuwane do innej puli.
Aha, czyli
Robimy na tym następną prezentację.
Jak robimy
Dobrze.
Następne dyskusje w kuluarach.
Dziękuję bardzo.